Okay, the next question that we got on the menu today is, what is the conjugate root theorem? Okay, so let's first talk about what a conjugate is. So a conjugate looks like this. Or conjugates, they're like twins, but not identical twins. So they're like twins. But they're slightly different. So conjugates is like, you'll have something like A plus B, and you'll have something like A minus B. These are conjugates of each other. Okay, what you can see is that the only difference is that the B terms are different signs. So B terms have opposite signs. A terms have the same sign. And a nice thing about conjugates is that, let's say you multiply conjugates together, like A plus B, and then multiply that with A minus B. Well, if we do the result of that, we're going to get like A squared plus AB minus AB plus minus B squared. You see how these are positive and negative, and they neutralize each other. So this is just equal to A squared plus B squared. So that's what conjugates are, and they're quite useful. Now the conjugate root theorem is saying that when you have complex roots, you'll always have, the roots will always be conjugates. So polynomial roots that are complex are always conjugates. Okay, so we all know and love quadratic formula. So if we have the quadratic formula, and quadratic formula is used to find the roots. And our roots could look a little something like this. We have like x equals b squared. Wait, it's not b squared. I'm just going to verify this super fast because sometimes it's not all on the top of the dome. So we have negative b plus minus the square root of b squared minus 4ac all over 2a. Okay, now we can rewrite this like this. X equals negative b over 2a plus minus b squared minus 4ac over 2a. Okay, now the discriminant, this part, the discriminant here, b squared minus 4ac. If the discriminant is 0, well, it's just going to be 0 over 2a. We're just going to have a single root. If the discriminant is a positive number, or underneath the root is a positive number, so b squared is more than 4ac, then we're going to have just like a regular number. So we'll have two real roots. But we'll have two complex conjugate roots if we have discriminant less than 0 or negative. discriminant, we'll have something like this. We'll have like negative, we'll have negative something. Let's just say that negative something is negative d is under here. We know that negative d is really the same as just like negative 1 under the root multiplied by the square root of d. And the square root of negative 1 is just makes the imaginary number so it just makes I multiplied by the square root of the rest of the determinant. Okay, so you can see how if that's the case, we'd have the two roots of the quadratic formula to be negative b over 2a plus minus I multiplied by the square root of the discriminant, not the determinant, that's a whole different thing, over 2a. And you can see how these would have to be conjugates of each other because we have the plus minus in between them. And because of the I term here, the imaginary number, we cannot just combine them like we would if we had a positive discriminant. Jeez. Thinking about my other math, doing determinants, but discriminant, it's got to be positive for them to be combinable. Because of that I, it's kind of like a variable. Like we can't just like combine them anymore. We can't just add them directly. So yeah, and as you can see, the plus minus makes it so that the complex roots are always conjugates. Complex quadratic are always conjugates as shown by the plus minus in the quadratic formula. Okay, cool. So if you ever calculate the roots of a quadratic and you find that the roots are complex but they're not conjugates, you know that they are wrong. It has to be conjugates for the complex roots of a quadratic. Yeah, okay, so the above solution is good. It's good. From quadratic, could be helpful.